Okay, and we're going. Okay, so last time we were talking about global extrema, and so I gave you all this theorem that basically the conditions of the theorem say that as long as none of this funny business right here happens, right? As long as we don't have open ends on our domain, or as long as we don't have an unbounded domain, and as long as we don't have discontinuities in the function itself, then really in some sense none of these scenarios can happen that will allow for an absolute maximum to fail to exist. And so here it is, the theorem. If these three conditions are satisfied, you have a closed and bounded domain, and if your function is continuous, then there is a global maximum of that function somewhere on your domain. It's a very useful theorem if you're trying to find a global maximum. Very good to know that it exists in the first place. Okay, all right. Now, we're going to move on now and talk about how to find critical points on boundaries. So we know how to find just regular old generic critical points. You take the gradient, set it equal to 0, pretty much, right? And then you have to worry about differentiability and things like that. But if you're on a boundary, things do get a little bit different. So now I'm going to hit the highlights of this example because ultimately this method that this example shows is not the best method for how to deal with this. It is, I think, the most it's the most obvious. This is what most people would probably try, sort of, not realizing that there's a more sophisticated tool out there, and it's good to know what that is. But in practice, day in and day out, this is not how you're going to do them. Right? So the big idea is, let's consider this example. We've got a function to maximize. And we've got a constraint set here. We're required to stay on this unit disk. And interior maxima, easy. Take the gradient, set it equal to 0. Critical point, no problem. Okay, but on the boundary, keep in mind the boundary is where this is an equals. Right? So the boundary of our domain is the unit circle. Notice that because x squared plus y squared is equal to 1 on that boundary, I can, in this case, I get lucky, I can simplify, I can simplify the formula for the function. Because the formula for the function and the equation describing the curve that I'm stuck on happen to line up in a very convenient way. So now that's just an initial lucky break. Look for this kind of good fortune. Sometimes it'll come up. Okay, but actually, you know what? I'm going to leave that there. But here we go now to really how are we going to find maxima on this boundary curve? And what I'm going to do is I'm going to break it up into chunks. We're going to look at the top chunk first. And I'm going to point out that top chunk is a graph. That means I can solve for one of the variables in terms of the other. And if I can solve for one of the variables in terms of the other, y, being as it is, square root of 1 minus x squared, I can adjust my formula for the function accordingly. And I can basically turn this multivariable function into a single variable function. Right? And then I just consider the appropriate values of x, right? X is going to range well between -1 and 1. So for every value of x between -1 and 1, there is a corresponding value of y. I can take the x and the y, plug them in, I get this single expression, and there's only one variable in it. And we know how to optimize. We know how to find critical points for a function that has just a single variable. You take the derivative, you set it equal to 0. So this will give you what you're looking for. But there's a couple of annoyances about this. For one thing, you're doing a bunch of calculus. That's a little annoying. Don't forget, of course, to check your endpoints. That's always something you have to deal with. And then, furthermore, keep in mind, what we did up here only works for the top half. There's also then the bottom half, where you have a different formula. Right? Different formula for y, which gives you then a different formula for your function, and you got to do the whole thing over again. So I think you can see that there's. Let me zoom out so we can see the whole thing together. Oh gosh, that still wasn't enough. So here is the work required to solve that problem with this method, and it's just a lot of clunky. So anyway, again, I want y'all to be aware of this, but I'm going to show y'all a much better way to do it. Starting pretty much now. Okay, so moving on. Section 4.3. So this is called the method of Lagrange multipliers. First, I want to define some terms and the category of problems that we're talking about. So we want to find the biggest value of a function, but with a catch. So this is not just the actual total biggest value of the function. It's the biggest value of the function among points that satisfy a requirement, what we call a constraint. Right? So altogether this is called constrained optimization. So easy just to see it with an example. Let's look at this question right here. You want to find a point on this curve. Here's a curve. On this curve that's as close as possible to the origin. Where on this curve is closest to the origin? Well, it's tempting to say that closest to the origin means I want to minimize distance. But do I just plain old simply want to find the point in the plane that minimizes distance to the origin? Because that's easy. That's the origin. Right? The origin has distance 0 to the origin, right? But very importantly, that's not what we're looking at. We are interested in finding, with the understanding that we're constrained only to look at these points. Among just those, which one is closest to the origin? So it's a harder problem. Everybody see that? All right. So one thing about these kinds of questions is there are actually two functions in play. You have to make an effort in your mind to keep these two different functions separate. On the one hand, there's the function that you want to optimize, right? Closest to the origin means I want to optimize, in this case minimize, this right here. And you'll notice I wrote distance squared instead of distance. And that seems wrong. Technically, I should be trying to find the point that minimizes distance. But I make the case, and this is a clever move, and I encourage you to do this yourselves. If you find the point that minimizes distance, it will also minimize distance squared. Because distances are intrinsically positive. Right? So the one that has the minimum of distance will also have the minimum of distance squared. Does that make sense to everybody? They're reasonable? Okay. All right. So why would I want to complicate things by squaring the distance? Well, because now I don't have to deal with square roots. And square roots are no fun. Okay, so there's this function that recognizes what it is we're trying to optimize. We call this the objective function. Okay. Totally disconnected from that, completely independent, is what we call the constraint function. In this case, the constraint function is this right here. Very importantly, the constraint function is the function for which one of the level sets is your actual constraint. And why level sets? It is an arbitrary choice, seemingly at the moment. It's going to turn out to be really, really useful when we get around to actually writing down the method for Lagrange multipliers. So for the moment, this seems like an arbitrary choice, but it is going to be important. So it's arbitrary, but it's important. Okay. All right, so two very different functions. Is everybody with me? Okay. So you want to make sure to distinguish between the function you use to define your constraint and the function that you're trying to make it either as small as possible or as big as possible. Okay. Alrighty. A couple other examples. So suppose you want to find the biggest possible box that you can make with a given amount of area. And let's make it a rectangular box so we can't get too geometrically creative. But biggest possible rectangular box that you can make with a given amount of area. So, for example, maybe you're working for Amazon and they're shipping stuff, and they cardboard's expensive. And they don't want to just go around using a bunch of cardboard they don't have to use every single time, multiplied by the number of boxes they ship on a daily basis. Oh my gosh, right? So they want to use as little cardboard as possible, but they want to get the biggest box they can. So reasonable optimization problem. Well, this is actually a constrained optimization problem. So you want to optimize volume. So volume is your objective function. This is what you want to make as big as possible. You want to get as much space in there as you can to put the most stuff as you can. There is a constraint, though. The constraint is area. Area is the thing that's fixed, right? You have a given fixed constant value. In other words, we're looking at level set of the area function. All right, so constrained optimization problem. Everybody with me? Okay. Here's another real-world scenario. Let's suppose you're running a small business and you want to, very reasonably, you want to maximize your productivity. Of course you do, right? And the thing is, we have a limited budget. We only have so much money. The sad reality of the real world. I've got a certain amount of money in the bank, or a certain size of a loan I'm going to be able to take out, and I'm going to have to spend some on labor, some on tools, some on materials. All together, wow, how do I apportion that amount of money to maximize my productivity? So again, constrained optimization. What we're trying to optimize is productivity. We need to have some formula for that, of course, to proceed. But that's what we're trying to optimize, with the understanding that we have a limited budget. The budget, then, is our constraint function, because, again, we have a fixed amount of money to work with. That make sense to everybody? Okay. So, constraint optimization problems are all over the place in the real world. Let's talk now about how to solve them. Big picture. The tool that we're going to use to do constrained optimization, the primary cornerstone underneath it all tool, is a process of elimination, just like unconstrained optimization. With unconstrained optimization, the idea was, if you can move in a certain direction and the function is increasing, well, the function's getting bigger as you go in a certain direction. Well, you can't be at the maximum if the function is in the process of getting bigger. So that couldn't possibly be the maximizer that you're looking for. That was our main tool, right? So in single variable calculus, if the derivative is non-zero, that's not the maximum, right? In an unconstrained multivariable setting, if the gradient is non-zero, couldn't possibly be the maximum. We're going to have a different elimination process here. And it's based on this theorem, observation, I'll call it right here. If we make a certain number of assumptions, and we're going to go through the details in just a moment, but if we make certain assumptions, we're going to be able to argue that the function is increasing as you move in a certain direction. And if the function is increasing, it couldn't possibly be the maximizer that you're looking for. So big picture, strategically, just like our previous optimization. Everybody see how that's, again, different details that we'll get to. But big picture, we're eliminating points by pointing out that the function's still increasing here. couldn't possibly be what we want. All right. Okay, so let's talk details. So we have this constraint set, right? Described by some equation, specifically as a level set of some function. It's the level set of our constraint function. So I'm going to need, for one thing, I'm going to need both of my functions to be differentiable. Again, keep in mind there's two functions. There's the objective function that you're trying to make as big as possible. There's your constraint function that defines your restriction. Okay, we're going to need both of those to be differentiable. That's just in order to make the argument work. Next requirement, the constraint gradient. Let's suppose that is non-zero. So here you go, constraint gradient. Gradient of the constraint function. Oh, yeah, hey, by the way, don't forget, our set is a level set of the constraint function. So we're looking here at the gradient of the constraint function, and we're also looking at a level set of the constraint function. And chapter 2 tells us that these are always perpendicular. Right? So in particular, if it's not a non-zero constraint gradient, that points in a direction, and that direction is perpendicular to our surface. Yeah? Everybody good? Flashbacks to chapter 2? Okay. All right. Next, the last assumption is that the objective gradient of f, is not a multiple of the constraint gradient. So, loosely speaking, it's pointing off in some other direction. If it's pointing in the same direction, it'd be a multiple of the constraint gradient. Right? So, if it's not a multiple of the constraint gradient, then it's pointing off at, it's kind of tilted off of that perpendicular. All right, so that's our setup. Is everybody with me so far? I claim with this setup, we're going to be able to argue that at the point that we're looking at the point where all of this happens, right, at the point where these conditions are satisfied, I'm going to be able to show for sure that that's not a maximizer. Okay, so here's how that works. Okay, there we go. Let's think about our objective gradient. That's this vector right here, and let's drop a perpendicular, as it were. Right? Let's look at the kind of, if you will, the shadow of the gradient of f. I'm going to call that the vector v. Right? So you look at the shadow, the projection of this objective gradient down into the tangent plane. Okay. Well, I claim that if you're at this point A, and if you're moving in this direction V, which of course, now keep in mind, you're stuck on the constraint set, but V is a tangent vector, and so you can totally just move along the constraint set in such a way that that's your velocity at a given moment. If you're at this point A and moving with that velocity V, the function's increasing. Easy to demonstrate that the function is increasing because I can just take the directional derivative in the v direction, and if you compute that directional derivative, don't forget we have a formula for directional derivatives. It's a dot product with the gradient, and you can just look at the picture. The gradient of f is that purple vector, and dotting it with v, which is that projection down there, and this dot product is, that's an acute angle, right? The cosine is positive, and that dot product is positive. So that means the rate of change of the function is positive, and that means increasing. Everybody with me? Function's increasing. It's not a maximizer. This eliminates A as a possible maximizer. Okay. All right. Feel free if you have a question. Everybody follow the reasoning? All right. So here's the really, really good news. This eliminates the overwhelming majority of the points in our constraint set. Said differently, these three conditions are satisfied almost everywhere. Not quite, but almost everywhere in the vast majority of cases. And so the vast majority of points we eliminate, and there's only going to be a handful left that we have to actually think about. The ones that are left, of course, are the ones where one or the other of these conditions fail. So if you want one or the other of these to fail, well, then you need one of these three things to happen. Either one of those functions fails to be differentiable, or the constraint gradient is not non-zero, aka it's zero, right? Or the objective gradient is not a multiple of the constraint gradient. In other words, it is a multiple of the constraint gradient, right? So what we're looking for, what we're going to call critical points, points where my elimination argument fails, points that are left over and that I don't know what to do with, and I guess I have to deal with them and check them, are just any point where any of these three things happens. And very few. There can be very few points where any of these things happens. Those are your critical points, and then you just check them. How we doing? Is everybody okay with that? Yes.
I wonder, is there a graph for f function?
Is there what now?
A graph for f function.
Oh, see, I can't really draw a graph of f right here because you'll notice from my picture that this is a kind of a three-dimensional picture. That means that these are functions of three variables. So I've got f is a function of x, y, and z. And so there's if I were to draw a graph, it would be a four-dimensional picture, and I can't do it.
Also, is there a level set for f?
Yeah, you could draw level sets of f, sure. It's pretty challenging artistically, and so that's why I'm choosing not to do it. And there are points of view that you can take by looking at level sets of f, and of course we're already looking at a level set of g, and you can make clever arguments about, well, what you really need is for those level sets to be parallel in certain ways. So there are arguments that you can take in that direction, but I think they're not only are they harder to draw, I think they're harder to understand. So if what you're looking for is, if only we could see a picture, it would make it all make more sense. I don't really think that's a good way to go. I think it's more confusing and not less confusing. Yeah. So it's fundamentally a hard thing to visualize just because of the dimensions involved. Yeah. All right. It's a good question. Yeah.
Sorry.
Yes.
I have a question about the elimination. If there exists a vector V such that the dot product is larger than zero, so we can eliminate the possibility that it's the existence of the vector V.
Well, yeah, that's right. But the fact that vector exists is an immediate consequence of what I'm allowed to assume, right? So the gradient of f, I'm assuming that it's not a multiple of the constraint gradient. So the gradient of f cannot, let's see how to draw this. It cannot be any of these. It can't be there, right? Because those are the multiples of the gradient of g, right? And so if the gradient of f has to be something different than that, it's going to have to point kind of off of that axis, and that means that there is going to be a shadow down there. That's what my v vector is.
Okay.
Yeah. Is that cool?
Yeah.
Okay. All right. So we've got tools. Let's see some examples. And here we go. Again, our three conditions for critical points. By the way, the algebra on some of these does get a little tedious. And that's the nature of the beast. It's not me making bad choices. It is intrinsically algebraically hard. So I'm not going to go through all of the algebra. What I'm going to do is I'm going to go to where I think the tricky parts in the algebra are. So I'm going to be kind of hitting highlights going through here. And that said, on an exam, you are going to have to do the algebra yourselves. So make sure at some other time to come through and think, fine-tooth comb and go through and make sure you understand and can reproduce, in analogous questions, the kind of algebra that's necessary for these. Okay. All right. So, constrained optimization problem. We want to find the highest point. Okay, greatest value of z. So my objective function is z. Okay. On a surface that has a certain equation, that equation is my constraint, and so the function whose level set we're looking at, keep in mind, constraints need to be written as level sets. They have to be level sets because I needed the surface to be perpendicular to the constraint function, and that only works with level sets. Okay, so this is a level set of g. What I've got written here is g as my constraint function. All right. Okay, here's some easy money. Easy money. These functions are polynomials. All polynomials are differentiable. Boom, you just earned a point, maybe two, depending on the details of the question. Make sure to get those points, right? These are conditions that have to be checked. Keep in mind there are three different kinds of critical points, three different sources for critical points, and it's okay to check and for there not to be any. It's not okay not to check, right? You do have to check. And easy to do, again, all you have to do is observe, hey, they're polynomials, they're differentiable. You just write down, boom, differentiable. And there's your point. Again, maybe 2 points. Don't leave that money on the table. Please make sure to actually do that. Okay. All right. Let's see. Next, we need to look at this condition. I need to find where the constraint gradient is 0. Side note, little cultural note, for reasons that are well beyond Math 219, sometimes this gets referred to as the degeneracy condition. There's really good reasons for this. We can't talk about it here, but this is called the degeneracy condition. Okay, so we need to check for degeneracy. We take the gradient of g. Quick observation, I can rewrite that with a little matrix algebra as this. Notice I need to, of course, set that equal to 0. That's degeneracy, is where the constraint gradient is 0. And check it out, we've got ourselves a little Math 218 system of equations here. Homogeneous, you notice. And we just need to solve that little homogeneous system. And conveniently, this matrix here, a little bit of arithmetic, you can check that it's non-singular, and non-singular, homogeneous, and all that. 0 is the only solution. Does everybody remember that from linear algebra way back when? Spring, whenever that, I guess. Anyway, so if you're a little shaky, perhaps on your Math 218, you want to brush up, make sure that this makes sense. It's a handy little tool to have at your disposal. Okay, so our solution then is just x equals 0. The temptation is to call this a critical point. Actually, it isn't. And the reason why is, keep in mind, we're only looking on the surface. We're interested in on this surface S. In other words, I'm only interested in points that satisfy this equation, and x doesn't. The origin, x equals 0, doesn't. So, we were looking on our surface here for, somewhere on this surface I need for a certain equation to happen, and we found a solution way over here. It's not on our, look at that, but I'm only interested in points that are on our actual surface, so we throw away this x equals 0 because it's not on the surface. Is that cool? So again, still no critical points yet. Again, don't throw away the easy money. Checking for the degeneracy condition, and even if you don't find critical points, again, the critical points themselves are not where the points, where there's dual use of the word point there. That's not where credit comes from, right? It doesn't come from critical points. It comes from argument, and this is an important part of the argument. So again, make sure to go ahead and do this, even if it doesn't result in actual critical points. Okay. All right. Lastly, here's what we call the Lagrange condition. Again, this is the third requirement right here. The third kind of critical points. And you can write down these gradients. In fact, you see we have them here and here. And you can take this, take this vector equation and write it out in coordinates. You get those three equations. But again, we're only interested in what's happening on our actual constraint. So if something, if there's a solution to the Lagrange equation way over here, don't care. It's got nothing to do. We're only interested in points that are on our given surface. So I have to add in the constraint itself. Don't forget the constraint itself. So all together, I have 4 equations and 4 unknowns, and this is where it gets, this is where it can get a little hairy. So I'm going to show you how to solve this one. I have 2 other examples that I'm going to show you. Again, I'm going to have to just hit the highlights because there's a lot of trivial algebra that y'all can do on your own. But there are highlights to be noted, and there are landmines to be noted, and I'm going to point out all of those. So, first off, okay, so we've got it down to we just need to solve this system. A temptation is to look at these equations and conclude that this must be true. I'm going to cancel the lambdas. Conclude that this must be true, and then, solve for x in terms of z, solve for y in terms of z, and take it from there, and we'll take it from there in just a minute. But I want to point out, we can't do this yet. I just glossed over an important point. And going from up here to down here, I canceled the lambda. You can't just go around canceling stuff. Canceling means dividing. You can't divide by 0. Right? You divide by 0, you're going to get into trouble. Right? For example, just to be silly about it, 0 times 7 is indeed equal to 0 times 3. That is not a problem. This is absolutely true statement. If you cancel the zeros, you have a false statement. You cannot cancel 0. Right? So, so I've got to establish, before I do this here, I've got to establish that lambda is not 0. And you'll notice that is what we get from this equation. You take a glance at that equation, notice, hey, if lambda were 0, that would I'm going to have 1 equals 0. Boom. Can't happen. Not a problem. Lambda is definitely not 0. Then I can cancel it and go on to solve the system. Everybody good? Everybody see the point there? Okay. All right. Now, once you have this, you can take this equation that involves 3 variables, and you can use these formulas to eliminate the x and eliminate the y, write everything in terms of z. That turns into this. Right? Remember, x is negative 1/2 z, so that, negative 1/2 z, etc. for the other terms. And you've got a big honking equation in terms of z. Solve for z. And once you know z, then you can solve for x and y, and that gives you your critical points. Everybody see what happened? Okay. All right. So, There's that. Okay, now next question. And I want to point out this next one is the question we've already looked at. We've already, we started the lecture today with what I introduced as a, bad method you're not going to want to use probably for dealing with situations like this. Now we have our more powerful tool. Let's see how our more powerful tool deals with it. So same objective function. Again, now looking just only at the boundary part of that previous example. So x squared plus y squared equals 1. Okay, so both differentiable. Sure. Easy. Right? We just earned points. Degeneracy. Not on our surface. So no problem. Curve, of course. This is 2 dimensions. So no problem there either. And on then to the Lagrange situation. So here's our constraint in Lagrange. Is this trio of equations? What do we do with these? All right. Here's a great tool. This applies in a lot of cases, a lot of Lagrange problems. Solve for lambda. You can see where lambda is going to come up. Lambda is always going to be a kind of a factor. You're never going to have e to the lambda, right, or anything weird like that. So it's usually easy to solve for lambda. And if you solve for lambda, like so, and like so, then the nice result is that those two things that are both equal to lambda have to equal to each other, and then you can find a relationship between x and y. And again, that's a lot of progress, and I'll show you where to go from there in a moment. But again, we kind of got ahead of ourselves. When I solved for lambda here, solving for lambda, notice you have to divide by x, and you have to divide by y. And anytime you find yourself dividing, you should get nervous. Oh gosh, what if the thing that I just divided by was 0? How do I know for sure that it's not 0? Well, in this case, we have to, again, just establish that in advance. And conveniently, this equation right here tells us that x is not 0. Because plug it in, see what happens. You plug in x equals 0, yeah, the equation doesn't work. Right? So that already tells you x is not 0. And likewise, this equation here tells you that y is not 0. So you got to write that down. No big deal. But then once that's established, then you can proceed to solve for lambda. Set the results equal to each other. And again, off you go. And it's all downhill from there. Once you have this relationship, you can plug that into your constraint equation. Your constraint equation then becomes that. Solve for y. That gives you your critical points. How we doing? Everybody with me? All right. Okay, last example I want to show you. This has got the biggest landmines of my examples here. So, got a constraint, big ellipsoid here. And I want to find the point closest to the origin. So, again, we have an objective function that's distance squared, just like a previous example. And easy to check differentiability, easy to check for degeneracy. Let's get down to where the landmine is. You write down your Lagrange and constraint conditions. You get these 4 equations. Again, I'm skipping over algebra. Make sure to fill in those blanks. What are we going to do, though, with this collection of 4 equations? Now, here's what a lot of students will do. A lot of students will say, clearly no critical points, because check it out. This equation clearly says lambda is equal to 1, doesn't it? Lambda's got to be 1 in that equation. And but here's the thing. Lambda's got to be 1/4 in that equation, doesn't it? Well, lambda can't be 1/4 and 1 at the same time. And furthermore, it can't be the 1/9 that it would have to be to make this equation happy. How could lambda be all 3 of these things? No solutions, no critical points. Lots of students would be tempted to write that down, and it's all wrong. It's dramatically wrong because, again, where did I get lambda equals 1 from? Well, I canceled. What if I'm canceling 0? How do I know x isn't 0? Maybe x is 0. We need to recognize the possibility that x might be 0. And in fact, x is 0 for a bunch of points. Right? So that's the problem. Now, what I can do here is say, look, they can't all be 0. X, Y, and Z can't. I mean, easily checked. If you just plug in zeros, this constraint doesn't work. So you can't have all 3 coordinates being 0. That means that I've got 3 cases that I can break it down to. And of course, these overlap heavily. That's fine. But one or the other of these 3 cases is going to have to be for whatever point I might be looking at. And you just take them one at a time. So let's take case 1. If x is non-zero, I can cancel those x's and conclude that lambda is 1. That's absolutely fair and square because I'm assuming x is non-zero. Okay, next. If lambda is 1, I can plug that into these 2 equations. If lambda is 1, then I've got 2y equals 8y. That means y is 0. And I've got 2z equals 18z. That means z is 0. Right? So, and I get that. And then I can take these, plug them into my constraint, and get 2 different possible values of x. Again, every one of these questions is different, but this is how it works in this case. In the x not equal to 0 case, I can conclude that x would have to equal to plus or minus 6. And then, now that was just one case. It's totally analogous in the other 2 cases. And grand total then, there's 6 critical points. So that's why I say this is the worst landmine. This is the nastiest landmine of the 3 examples. One little careless, oops, I accidentally divided by 0 causes you to miss 6 critical points. And of course, that would be absolutely catastrophic on a test. So be very, very careful, please, about those little algebraic details. Okay, questions? Oh, it looks like I went a little over. I'm sorry. But anyway, we're done with the material for the course now. Enjoyed having you all in the course. We do have the exam on Friday. See you then. And good luck studying. See you later.